Good afternoon, everybody. This is Kali, and we are going to, as you can probably tell, just from seeing the view, this is going to be more of that how to build atoms or nucleus, neutrons out of quarks. And if you build them a certain way, how interesting it is, what comes out of it. So, this is our toolkit. If anybody wants to build this along with me someday, that would be so cute. Okay, so up quark, 2 down quarks, 1 anti-up, and 2 anti-downs, right? Blue is positive in my modeling, and yellow is negative, and neutral is green. So yes, so let's build ourselves some particles. We're going to first build ourselves a proton. So for a proton, you need 1 up, another up, and a down. So we'll put this stuff aside for a sec. There we go. There's our materials. Now, first thing we're going to do is take these 2 parts here, a charge pair, and in the way I model it, it's like, just think about it, 3 fractional charges, okay? There's 3 dimensions to the universe. So, where'd it go? Our little Cartesian coordinate thing, 3 axes, 3 charges, 3 fractional charges. But what if there's we'll get into this later, because I think this is sort of how the universe works. It's like layers, 3 layers of things, each of them 90 degrees to the previous one, which is why you can have an electron. And then you have a muon, same charge. If they took up that much more room or changed the volume of space that they modified, then wouldn't you think the charge would change? But instead, just somehow the tension, the speed of what's going on in there changes. So what if instead it's like a Banach-Tarskian backwards, and there you have your electron? Okay, I made a giant one because electrons surround things, but you have your electron, and then in the same space, but initially maybe 180 degrees to it, okay, spins the other part, the duplication, the second layer, which is the muon, which would be exactly oppositional. It's like, so it's like spin pairing with electrons in a nucleus. Only before that, when you're first making a quarky thing, you can fit 3 of them, right? You can fit a tau even. So there's like 3 electrons all in the same space. But if they all have a Coulomb force, then you've just tripled the, you have cubed what's going on in here. First you squared it by making a muon, then you cubed it by making a tau. So no wonder the energy is so much, because it's that much movement crammed into the same amount of space, or the same amount of using up of volume of an electron. So anyways, this would be an electron, which is 3 directions of outflow or inflow, divergence, 3 dimensions of a divergence. But I get ahead of myself. Let's get back to making a proton. So we're going to make a proton. We're going to take these 2 things and we're going to squish them together and make a positive charge and a negative charge. I know what I can make with one of those. I can make a photon with one of those. Let's call this a photon. This is an unusual photon because it's a very high energy photon. This photon has the wavelength of 2 pi Planck length, which means it's trapped over its own gravity. It's so small. It's like it couldn't expand because it stopped there. It's the initial singularity. It's the minimal attractor for singularities. Anything smaller than a black hole would decay into this. It would be this is my way guesstimations, but following the rules of geometry, perturbation would cause it to decay into a bunch of these, or one of these individual neutron or individual mass photons. Okay, so we made a mass photon. There's our mass photon. And now we have 3 directions of charge, right? 3 dimensions, 3 charge components, makes sense. And then I would put this in the middle. So that's what we're going to do. And there's my proton. And then, yes, and there's a proton, right? 3 axes, 1 for each of the EM fields, static, electric, magnetic, right? 3 types of neutrinos too, but we won't get into that quite now. 1, 2, 3, ow. And it tumbles and oscillates. How weird. So proton. And the way I would draw a proton, and if you ever come across my notes in Adobe, which I don't have access to anymore, I can only look at them, I can't modify them. But in there I use yellow. I don't have a yellow marker, so I'm going to use red. So a proton, right, would be blue, right? First we took a, do I have green either? No, we're using black for that. Okay, so first we took one of these, one positive charge and one negative charge axis, canceled them out, made a photon instead. That's the little green ball. So this is going to be our green ball. I know it's not green, I don't have green. What can I say? Okay, and then we had left over 3 axes of blue, positive, 3 axes of blue. That's why I make the diagrams like that. So it's like basically like Cartesian coordinates, and then you can tell what charge is on each of the ends of the axes. And someday I might go into all the weird particles, but most of them decay so fast that they're not worth paying attention to, in my opinion. So there's a proton. Now we're going to make a neutron. And for a neutron, what we need is one up and 2 downs. And there we go. Ooh, actually. One up, 2 downs. So I'm going to take this and make a photon. Boop. Photon. Mass photon. I'm going to make these 2 and make another mass photon that's just in orbit around that mass photon, which means it'll be a perturbative orbit, and sometimes it will decay. Like if it's not in a strong gravitational field, it would decay like a neutron does. And because that mass photon is, it's charge components, right? So anyways, we're going to put these charge components, boop, and we're going to wrap it into a second layer, and now we have a neutron, which is 2 photons in orbit over each other, sort of. Or it might be a spin coupling thing again. So if the positive is opposite the positive always, and the negative is opposite the negative, you could have 2 photons occupying exactly the same space, same way the muon I was talking about with the charge. And it would sort of be a phase relationship. But regardless, I think the best way of looking at it is that there's a photon, mass photon, and then there's another photon, mass photon, in orbit as well. Because now what we're going to do is we're going to have this neutron decay. So I'm going to take this neutron and I'm going to go and break it open. And when it breaks open, what you end up getting, miracle, is a proton. Everyone knows this, right? A neutron decays into a proton, an electron, and a antineutrino. So I took that neutron and broke it into a proton. And an electron. Like how I made that, and it's like sort of, I know it's not perfect, but so see the electron surrounds, because that photon that I had made previously, right? I took those two charges and made the second photon. Well, I broke that photon apart, and somehow that photon turned into a whole electron. And a positron, and the mass unit still. So this would be a hydrogen atom. 3 axes of positive charge, surrounded by 3 axes of negative charge, and with a mass unit holding the whole thing together. So yes, so there's a proton. There's an electron. We can just, maybe I can rest it under. Does that look cute? Yeah. Boo. And then a neutrino. Because when it was a photon, right, it was spinning. But when it decomposes, this isn't a spinning charge. This is a radial charge. It's a negative charge. And this is a radial positive charge. So where did the spin go? Well, the spin went into the neutrino. And so this spinning swirl in space, which doesn't have an inflow or an outflow, so it doesn't have a charge. It's just a spinny thing that spins in all 3 dimensions all the time, like I was talking about. And so you can never tell what it's going to be. Like it goes, oh, it's a this kind. Oh, it's a that kind. Why? Because one of these axes was associated with the charge, with the electrostatic. One of these axes was associated with the electric, and one of these was associated with the magnetic. So as it literally tumbles in space, but it's moving near the speed of light, right? So even if it's tumbling almost at the speed of light, the phase interaction between the speed of motion and c, the tumbling of the rotation, would end up being what we see as neutrino oscillations, right? It's like the modulus between the spinning of this, which is c probably, and its speed of motion through space, which is always decaying and becoming less and less of c. And therefore I would imagine this would speed up, but maybe it slows down, who knows? I could be wrong, things are contrary. But anyways, so there we go. There's a sort of like rambling long take on how things decompose and how I see charges, and this whole thing about why there's 3 fractional quark charges is to set up the 3 dimensions, the 3 relative axes. And if you want, you can always fit 3 layers of spin in the same space, right? There's 3 layers of electron. You can fit an electron. Then you can also fit a muon, and then you can also fit a tau, if you want. They don't hang together. The pressure's too high. It has to be extreme conditions to hold them together. But it is possible. No doubt the same with, of course, the others. So, which is why the neutron can actually be the same size, basically, as the proton, because this is 2 photons, which means that there might be a form, or is it just at the event horizon, where there's 3 layers of this? Like when a neutron hits the event horizon, right? It's like, oh, there's 3 layers for a split second, but you can't hold that together because you've got too much cram. That's maximal. That's a genius point. It's going to be actually triple layers because the neutron is a double layer itself. So for that brief moment, you've got a triple layer. Anyways, my rambling thoughts on how to construct particles and why particles are constructed like that and why there are the 3 quarks and things. Peace. Okay? Don't worry, the future is going to work out just fine. Okay? We can make sure it does, just I'll make good choices at each moment. Okay? We'll try our best. And if you make a bad choice, you go, hey, that was a bad choice. Next time, let's try and do better, colleague. Okay? Peace.